So now next is Nick, and without losing much time, over to you talking about counterfactual things.
Yep. Cool. So as Kayhan touched upon already in his very introductory talk, and Daniel mentioned, an interesting question that we can ask with causality is this question about counterfactuals and reasoning about hypothetical outcomes. When we then look at this ladder of causation, which is like one of those things that Pearl mentions a lot, this is from the Book of Why that Ben also recommended as a holiday season reading. You can think of the different levels that causality enables and that what we're doing in machine learning. Most of that is on this first rung of the ladder, which is just this association rung, where you only reason about observation or do correlations and predictions. But with causality, we can do so much more than that. And this first thing was this example that Kayhan brought, where you actually interact with the environment around you. You do something, which is exactly why the do operator is called the do operator, where, for example, you go to your sprinkler and you turn it on and you make sure that your sprinkler is on, and because of that, something would be wet. But this last rung is this reasoning about this hypothetical worlds, where you think about, oh, so if I would have done something else instead, how would this outcome have changed? And this requires both an understanding of the world around you, how you currently perceive it, but also about the inherent causal directions and mechanisms that then actually apply those changes that you would make. To then formalize this, we're talking in our framework here that I'm going to be mentioning. We're using structural causal models. This is also, again, a very Pearl-like theory and not necessarily directly, well, there is an equivalence between the potential outcomes framework that Christine was mentioning and those structural causal models, but the formalization is slightly different. And we're going to focus on this one here, where basically you have a directed graph, which is a causal graph, where you have random variables x1 till xm, and you have mechanisms which specify those variables. And you then also have each of those variables has a parent. So for example, when we look at, let me get my pointer, when we look at V here, for example, V has A and B as its parents, which then cause V, the value of V given some noise as well. And this is the important part about structural causal models, that you also have this exogenous noise variable, which is some inherent noise that you can't model away by just the parents or something. This is something that is unobserved. And for every random draw that you then have from this distribution that is induced by some parents, you have an instance of this exogenous noise variable, which basically captures the state of the world and captures everything that's uncertain, that is still left uncertain given you observe your parents. And you can then factorize them, as Kayhan showed earlier, that you basically can factorize each variable only to be dependent on its parents. But then we can do operations, for example, setting one value in your graph to be constant. So how do we then actually do counterfactual inference with that? And the first step is this abduction step, as it's called, where you start with inferring the state of the world. And basically, you have a set of observations. X in this case is basically you observe all the different variables in your graph, and you ask the question, what noise variables actually did cause my observations? If you then have those exogenous noise variables, you can have an identical mapping between your observations and those noise variables and can reproduce your observations. If you then have your graph and your noise variables, you can then do an action and actually interact with your world, or as in do this hypothetical action of changing, for example, a mechanism or changing one variable or multiple variables in your graph to be a constant, which is this do operation where, for example, we take this V that I described earlier, you just set it to a constant factor and it gets disentangled from its parents. Once you did change your graph and also infer the state of the world, you can just do forward propagation in your graph to actually predict your counterfactual outcome, which is the same as you would do when you just sample from it, but you just fix your noise variables and also then change the graph by an intervention. So how do we actually do this in practice? And for this, we wanted to make it usable for medical imaging, which means that we need to work with very high-dimensional data. And classical structural causal models usually only use linear models, which means it's really hard to actually then make them work for medical imaging. So instead, we wanted to use deep learning mechanisms, and we decided to look into deep generative models that also allow for tractable inference of those noise variables, because a lot of the existing literature out there simply did not care about this abduction step, which means that you can do interventions which don't require knowledge about the state of the world, but only about your causal graph. And this is a small side note, we are focusing on the continuous data case, but our models technically also support discrete data, and it's just a little bit harder to do the full intervention then. So how do we do this? And I'm going to focus on two models that we are actually using in our experiments. We also had a third one in the paper, but this is something you can read up on later if you are interested. So the first, and this is the easier one of the two, is you can use normalizing flows as invertible assignments. So as I mentioned, that you have those assignments that define each variable in the graph, given its parents, and then also its noise variables. So if we have this easy case on the left here, where you have an observational value in your graph, you have its parents, and then you have the noise variables over here. So you condition this assignment on the parents, and then you have an invertible mapping between the state of the world, the exogenous noise, and this observational variable in your random variable in your graph. And because normalizing flows are fully invertible and you can simply train them with maximal likelihood, this is relatively straightforward. There are some practical issues with numerical stability, but this is not important right here. The second one though, and this is the issue that normalizing flows bring also, is that you can't change the dimensionality of the data, as in xk and epsilon k need to have the same dimension, which means that if you have big images, all this assignment needs to keep that dimensionality, which is just very memory intensive and not practical. So we then decided to look into variational autoencoders and then combining them with those invertible transformations, where we allow to first encode your data into a lower dimensional latent space, which captures the high level information about it. And we then combine this with the parents to actually condition our invertible transformation, which then gives you an invertible transformation between this high level noise, which captures those like fine-grained details, and the actual observation. And this can be trained similarly to just a normal variational autoencoder using the elbow and following the autoencoding variational base algorithm. So this then actually allows us to do cool counterfactuals, and we've done a case study on brain images. So basically, we've been looking at the UCO Biobank dataset, where we have a lot of brain scans and a lot of also correct data, side information about it. For example, age, the biological sex, the total brain volume and ventricle volume. And then we also decided to not work on 3D images, but rather 2D slices simply for memory concerns. But everything should scale to 3D as well. And as a side note, and this is especially important after Daniel's and Ben's talk, we're actually using the brain and ventricle volume only as derived information from the 3D segmentation. So the causal assumptions that we're taking here are not necessarily correct, but this can be a discussion for later on. So we then model this as this graph that we can see here, where we basically say sex and age have an effect on the brain volume. The brain volume and age have an effect on the ventricle volume, and then only the ventricle volume and brain volume have an effect on the actual image outcome. And as you can see, this is the more explicit graph where we added the exogenous noise variables as well. And it's very clear that each noise variable only has an effect on its corresponding random variable in the graph. Most assignments here are model as normalizing flows. Those are those two-sided arrows. And then we have a variational autoencoder part for the image because it's this high-dimensional part. And given this, we can then train this using standard variational autoencoder elbow techniques and then do counterfactual inference, actually, which works surprisingly well. So those are a couple of images here, two examples as original images, which are in the leftmost column, where we have two 2D slices. The first example is a female brain, which is around 50 years old, and the second one is a male brain, which is about 70 years old. And going from left to right, we do different interventions on the causal graph, and then calculate the counterfactuals. And we can show that, for example, going from a female to a male brain, or a male to a female brain, we see a change in both the brain volume, which is, you can see as this color change in the difference maps. So the bottom, the intermediate rows are always the differences between the original image and the actual counterfactual image. And we see that, for example, from going from the original image to as being female to a male brain, we see that the brain volume actually increases, whereas going the opposite way, we see that the brain volume decreases. And the same then goes for the ventricle volume here and there. It's not that easy, I guess, to see on those images themselves, but it's much easier to look at the difference maps. And we can look at then, I guess, much more extreme examples, which is relatively easy, for example, for the ventricle volumes, where you can see that when we make them smaller, they actually go smaller, whereas the brain itself doesn't change that much. And we can also make the ventricle volumes much, much bigger than we all observe in the actual training. And then the ventricles grow bigger, but the brain itself does not change that much either. And the most exciting bit here potentially is that we keep person identity the same, which means that actually when you look at the folds, they are actually basically the same throughout all the images. And they're also different when you look at different original images. So we actually keep the folds in the brains more or less the same, which is because we disentangle this high level and no level noise, which makes this very straightforward to keep the identity. So lastly, this is just a nice plug. I'm not going to show the live demo right here because it's going to take too much time, but this is something if you're interested and want to play around, there's all the code for this is online. And we have a Colab online also where you can just change a couple of sliders and you just straight away see how things change. And this is also where you can kind of see changes much, much easier when you have the original image on one side and then the counterfactual one on the next. And then also have the time component to it. So lastly, I guess we've seen through different talks before already also that causality gives us a language and also tools to hypothesize about different potential outcomes. And our deep structured causal model framework fulfills all ladders of the causation by Pearl. We can generate tractable and also very plausible high-dimensional counterfactual images that we've seen on this brain example. But we still have some caveats that we actually are more on the counterfactual causality side of things, that we currently assume that every random variable is observed, and that we also need more research on the identifiability side of things, which is something that Kayhan touched on in the very beginning. This is my part, and Kayhan is going to talk about his paper next. Small blog, all of this was just accepted to NeurIPS, so check it out over there and read the paper if you're interested.
Thank you, Nick. Just a quote from the chat. Holy smokes, this is awesome. Someone said this. So Kayhan, over to you. Thank you.
Sure. Can you hear me?
Yes.
Okay, that's great. So thank you very much, Nick. So I'm going to talk about another application of the counterfactual. This is basically the work that done by my student, Sumedha Singla, who's a PhD student in the University of Pittsburgh, working in my lab. So we basically use counterfactual for explaining the black box, and then we call it basically exaggerating the effect. All of us know that opening the black box for medical imaging application in general, healthcare application is very important for two different kind of reasons. One of them is real deployment of such algorithm, because healthcare application involve high risk domain, and sometimes these conditions are rare. And if our classifiers or our black box focuses on spurious features, it can have perhaps lethal consequences. It's also important for medical research. Sometimes medical research really is not about prediction, is also about understanding. So we want to relate, for example, what we see in medical images to other types of data, such as genetics. So we want to open a black box and see that what new insight this black box can provide us. Now, the question is that how can we open this black box? There are lots of papers in computer vision for opening these black boxes that produce different outcomes, and most of them produce attribution features or heat maps, or like so-called saliency maps. So here I'm showing examples of two conditions for X-ray images for cardiomegaly and pleural effusion, and each of the columns are different methods. And as you see that it creates a heat map, but it doesn't, it tells you where in the image is the black box is looking at, but doesn't tell you why. And most of the time we are interested in why. And in these specific examples, actually for two different conditions, there are similar heat maps. So it's not really clear what really the model is looking at. So my point here is being that really salient map for medical imaging application is not enough. So our general idea was basically started based on a discussion that we had with one of our clinical collaborators. And when we showed him one of these heat maps, he said like, oh, no, don't show it to me, remove it, and tell me like what should change in an image so that it change the mind of the black box. So we thought about it is that wouldn't it be nice if we have some sort of like a knob that continuously change the decision of the black box, and then it tells us what would have happened, what changes should have been in the image to change the mind of the black box, as if that you're exaggerating the effect of the disease or de-exaggerating the effect of the disease. So, so here the counterfactual would be that if you put an image into black box and produce an output value that is here somewhere in between 0 and 1, which is the posterior probability of the prediction, what would happen if I perturb the output value a little bit forward? So we are basically viewing the explanation as some kind of a function that accept an image and accept this amount of continuous perturbation and generate a new image or counterfactual image. So here I'm going to tell you how we are going to make this counterfactual example using a toy data and explore the other possibilities of using this kind of counterfactual explanation in detecting biases. And then I'm going to show you application of that on chest X-ray and how we can use it for explanation and finally conclude. So let me construct it. So as I mentioned earlier, we are basically viewing this explanation as some sort of a function. So I'm given an image and I want to provide this knob to my user so that this knob, which is output of this black box, it can play with it and generate a new image. So we thought about that, like, okay, if this is a function, what kind of criteria it should satisfy? So one of the criteria that should satisfy is that it should create a realistic looking image so that it can interact with human. It should also be compatible with the black box, meaning that if I go from, for example, left to right smoothly, the output of the black box should also change smoothly. The other important properties is a self-consistency. It means that if I move the knob forward and then bring it backward, it should create the same image. So give you an example, in this toy example, let's say that I'm given image of this person, and the output of the black box is that this person is smiling or not. So the equivalence of changing this knob is going from not smiling to smiling, and as I go from left to right, the person starts smiling a little bit. So of course, the method can be applied for output of the multi-class classification and multi-labels, but let's focus on binary classification. The output is posterior probability. I'm going to construct it gradually. So as I mentioned here, the objective that we have is to generate this knob. And then this knob is that given an output of the black box, we want to have a delta perturbation. So as I change this delta and I plug that into this black box, it creates different output for me. So one way to construct that is using basically a sort of conditional GAN. That the conditional GAN basically accepts an input image and encode it to lower dimensional representation. And in addition to that, accept this delta distribution, which is amount of perturbation. Both are passed through a generator to create a counterfactual image. So in order to ensure that the first condition, which makes the image realistic looking, satisfied, we are going to use basically a variant of the conditional GAN we developed for this purpose. And this basically, this implicit way of modeling the distribution ensures that the resulting images are realistic looking. The second condition is compatibility with F, meaning that if the current output of the classifier is Fx and I want to perturb it by delta, the new created image is, if I call it X delta, which is a counterfactually generated image, if I plug in back to the black box, the amount of this difference between output should be delta. That can be easily enforced by a KL divergence between the output of the perturbed image and the delta perturbation of the output of the original image. And finally is a self-consistency. The self-consistency can be viewed as two-pronged. So the first one is that if the delta is 0, the image should be reconstructed back. And the second condition is that if I create an image which is delta perturbed forward, if I make the delta to minus the delta, means that if I change the perturbation forward and then make the perturbation backward, I should create the same image back. This is so-called cycle consistency and can be added as an extra loss function. So so we developed this model and said that, okay, so it does what it's supposed to do, and like we have shown some results, but what other interesting things that we can do? Is it possible to detect hidden biases in a data? So in these toy examples, we created 2 data sets. In one data set, we create a simple classifier that detects the persons are smiling or not. And in one of the data set, the genders are balanced, and in the other one, most of the male subjects are smiling while the female subjects are not. So if this type of counterfactual explanations are actually useful, in one of the, if I have 2 black boxes, one trained on the bias data, the other one is not trained on the bias data. If I given the same image, if I create a counterfactual for both black boxes, if I go from left to right, on the bias data, the male characteristic starts showing up, indicating that this black box is biased. And this can be used basically as a tool to interrogate this type of black boxes. Now that I've shown you some examples on these toy examples, let's see how it performs on our data sets. So as I mentioned earlier, really saliency map for medical imaging only tells you why, but doesn't tell you how. So in these examples of the chest X-ray, we are focusing on pleural effusion. So if you actually talk to your clinical collaborators that how do they diagnose the pleural effusion, they will tell you that they usually look at the boundary of the lung, and they see that if they see the sharpness of the boundary of the lung, or they don't. So here in these specific examples, we have a positive, so it means that this patient is pleural effusion. And we created counterfactual image both on 2 extremes of this basically a spectrum, one going all the way toward normal and the other one going all the way toward abnormal. And as you see, and if you are going completely toward abnormal case, if you look at the boundary of the lung, this curvy structure starts showing up, while on the normal subject, the boundary of the lung is sharp. Basically, it means that the counterfactually generated image satisfies what the doctors actually expect from the images. So as I go toward normal, the boundary of the lung become more sharp, while as become going toward more exaggerated pleural effusion, the curvy shaped structure, which is, I guess, suggesting the position of the liquid in the lung, shows up. And in fact, you can subtract the normal and abnormal, so two extremes of this counterfactual, and create a new heat map. And the new heat map is basically can tell you that where in the image and the changes are happening. So our method can produce both heat maps and also tells you where, and can also tell you how. Another interesting direction was that we thought that, okay, so in order to evaluate this type of model, beyond just visual explanation, one way to perform this task is to use some definition of the disease that are clinically acceptable. So some of the clinicians, so here I'm giving you two examples. One is cardiogenic edema, and the other one is non-cardiogenic edema. And in one of the conditions, what the doctor is actually looking at is basically the size of the lung and relative to the size of the heart relative to the size of the lung. So this is called CTR. While in cardiogenic edema, the CTR value changes. In a non-cardiogenic edema, this value should stay constant. So we thought that might be a good metric for evaluating our method. So this is basically an example. So for both of these two images, I'm presuming both of these two images are basically normal. And then we said that, okay, what would happen if I apply this counterfactual on both normal and abnormal size? And as you see that for as I go toward more abnormal explanation, this CTR value start changing. So meaning that the model, the black box is encoding some information that is sensitive with respect to this CTR, although this CTR is not actually used in the model. And this basically the resulting the heat map that is basically a result of subtracting abnormal to two ends of the spectrum. While if you perform the same task for non-cardiogenic edema, the CTR value stays the same. Another cool properties that we observe is that there's a kink on the boundary of the lung and the heart that they do actually look at, and it actually shows up in our method. And it basically suggests that this specific black box is looking at what it's supposed to, and it can provide, like, in addition to where, and actually explain why that region is also important. And finally, we can create this animation that, like, if you go from one end of the black box to another end of the black box, for example, in this case, a cardiomegaly, which is enlargement of the heart, abnormal enlargement of the heart, as you see that you can create this animation. As you go from one end of the spectrum to another end, the size of the heart increases. And basically, it provides another visual explanation of the black box to the doctors. And to conclude, so the saliency maps for explanation in medical imaging context is not sufficient, because we can only tell you where, but not why. And we do need to know why in order to interrogate these type of black boxes. Counterfactual explanation is an example. So in this specific case, we view the counterfactual explanation as a function, and we show the potential application for detecting bias, although that needs more work. And finally, we showed that the visual explanations are consistent with clinical expectation. This, the previous version of the work is published in ICLR 2020, and the code is publicly available, and there's a much extended version of that is coming that hopefully hit the archive in 2 weeks. Thank you.